got two ways of doing this. We can either go straight through, or we can pick the easy ones, knock them out first, which is how I would recommend you do it on the test. Do y'all have any preference? Strong feelings?
Is this the only time we're going to be able to review, just this class period?
I don't know. We'll try to see if we can fit something in tomorrow or after school or something a little bit. Okay. Any preference?
Easy ones first?
Yeah, let's go ahead and, I think we should do that first. Alright, so I'll keep a little note on which ones we've taken care of. Alright, go ahead and hit the record button there, Miranda. Alright, so let's go ahead and start at number 2. This one says find all possible functions with the given derivative. Okay? So, what that means is, this is the derivative. What you're looking for is the original function. Okay? So, we're going to basically be using integrals. Are y'all familiar with integrals?
It's just the same though.
Okay. All right. Let's go with the forward way of speaking first. Then, okay. If I have any function y equals a times x to the b, okay, and you were wanting to find the derivative, so you're wanting to find y prime. Are y'all familiar with the power rule? The way of
Yes, you would do like b times a.
you would already
Yeah.
we say drop down, power down. You drop down the b, so b times a times x, and then the power down,
b minus 1.
b minus 1, right there. Is that looking familiar? An example of this is if you have y equals 3x to the 5th, then the derivative y prime would be, you bring the 5 down, so 5 times the 3 times x, and then you power down, the 5 turns into a 4, and so you have y prime equals 15x to the 4th. Is that looking familiar? Okay, so this is what I would call the regular way. This is going from a function to its derivative. In this particular problem, they've given you the derivative, and they're wanting you to find the original function. Okay? Have you all done homework like this before? Yes. Okay. All right. So we're in this case we're going the opposite direction. Okay. So that might lead you to think that you need to probably do some sort of the opposite operations, and that's correct. So for instance, normally we bring that b down. Now we probably need to bring the b up. We've got a minus 1, and so now we need to kind of probably have a plus 1. Okay. So maybe it would be good just to do just a short example here. So what if I just had y equals x squared? Y prime would be 2x to the first. Okay? So think about what you would do in order to go from here to here. What you normally would do is you would take that 2 and basically that's going to be this value up here. So going from here to here, not too bad. So just bring the 2 up there. All right. What about this? What if I had y equals 3? That's one I had right there. 3x to the 5th. Now this is, yeah. Just go back and show that one. You might think, based on looking at this, that the solution is every time to just put the exponent there and you're done, right? Just move this up here. However, that's not going to work in situations like this where you had a multiplier out front, okay? In that case, if we had 15x to the 4th, and we're trying to get up here x to the 5th, what's going on here? Well, it looks like we'd go from the 4 to the 5, so that would be like sort of plus 1, so you do some sort of power up process. And then going from the 15 to the 3, well, that seems like I would divide that by the 5. Okay? So let's do another example forwards and then look at the reverse just to see if we can notice a pattern here. So y equals just say 4x, I don't know, to the 10th. Someone other than Emily here, what would be the derivative of that?
40x.
Okay, 40x to the 9th. So let's think about what's going on if we're going from here to here. Looks like that exponent gets bumped up by 1. That's going to take care of the 9 to the 10. And here we've got a 40, and we're going back to a 4. So that looks like you'd have, if you went and had the 40 divided by 10, then that's going to give you 4. Over here, if you look like we had the 15 divided by the 5, that would give us the 3. Okay? So that makes us kind of think if we have y prime equals b, I'll make it a times x to the b, then this is what's called the antiderivative, or the original function rather, is going to be x to the b plus 1, and then the multiplier is going to be that original a divided by b plus 1, divided by that new power. We saw that's how we could get the new coefficient by taking that 40 and dividing it by the 10, which is the exponent there. It works here. The new exponent is 5. Dividing the 15 by 5, you get the 3. It also works over here. The new exponent is 2. Taking our coefficient here, 2 divided by 2 is going to give us 1. So this is the antiderivative. This is the power rule for the antiderivative. Okay? Instead of pop down, power down, where you brought this down and subtracted by 1, it's the complete reverse operations. You add 1 to the exponent and then divide by that. Okay? Now, that should help us here with the 3x squared, because, so we've got y prime equals 3x squared plus 5. So the original function, y, must be, see if y'all can apply it.
X to the 3rd plus 5x.
To the 3rd, okay. Yeah, I'm going to go ahead and write those other things to make it a little more clear. So we've got the 3 is from here, bumping the 2 up to 3, and then dividing by that new power 3. Absolutely. Now, yeah, plus, and you said 5x, okay, because technically you can think of this as x to the 0 power, okay, there's no, it's a constant, and so x to the 0 would then be x to the 1 divided by 1.
And then would you put plus c for the constant?
Yes, you're going to put a plus c, because you're like, what in the world, right? Why are we putting a plus c here? It seems like a bunch of random rules when I'm kind of teaching it backwards like this when we're going through problems, but that was what he was doing last several weeks. So, a reminder here that if you have the original function is, I don't know, 6x plus 10. Roger, what's the derivative here of 6x? Well, there's an invisible 1 right here, so let's pop that down. Okay, so 1 times 6 is 6, and then it would be times x to the 0. So x to the 0 is 1, so that's effectively 1. Alright, and now somebody tell me what's the derivative of 10? 0. The derivative of any constant function is 0. The slope is always 0. So we have y prime equal to 6. Okay? It gets interesting when you think about this. And this is why you have to have that plus c. What if instead of that I had y equals 6x plus 20? It would be. The derivative would be y is equal to 6. The derivative of 6x is 6, and the derivative of 20 is 0. So, they're like, okay, y prime is 6 and y prime is 6. No big deal. Except when I tell you, hey, y prime is equal to 6, what's the original function? Yeah, you're like, well, I don't know. It could be 6x plus 10 or it could be 6x plus 20.
Well, that's why you put the C's.
And that's why you put the plus c's,
In
because
the
it's
number.
constant. It could be plus 10, it could be plus 20, it could be plus 15.5. I don't know what it is. So anytime you're going from a derivative back to the original function, okay, I don't care how many terms there are, you gotta put that plus c because you don't know what other things could be there. It could be anything. That c is called the constant of integration. Okay, so final answer here, 3x squared, or sorry, that's the original problem. X cubed plus 5x plus c. Alright? I'd rather make sure everyone's rock solid on a few of these than sort of weak on all of them. This is an antiderivative problem because we're giving you the derivative and they're asking you to find the function. So we're doing that antiderivative process. I always like, I kind of tend to be visual. I always visualize the original function up here at the top and then the derivative right below it. And if you want to think of the second derivative, you can think of it below that as well. Other questions? All right, let's find another good one. That one's not too bad. I'd like for us to practice some more derivatives, and this is a good one because we're going to get lots of practice with derivatives on this guy. Okay? So this says find d squared y over dx squared. Does anybody recall what that terminology is? It's a second derivative. And how do you find the second derivative? Yeah, derivative of the derivative. Okay. And here's our problem right here. 7x squared plus y squared equals 9. Okay, so this type of equation is what we call an implicit equation. You have explicit and you have implicit. Explicit is when they just say it the way it is. Just like those explicit lyrics, you know what I mean? It's sort of like, they're just laying it out there, okay? Now, implicit, like when something's implied, and you're not kind of saying it, but you are kind of saying it, but not straight out there, okay? The way that relates to functions is that an explicit function has y equals blah, 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 okay? And implicit, it's got the x's and the y's all kind of mixed and mingled in there, okay? And yeah, that can kind of, you're like, it's kind of like hidden. Does that make sense? So the way that you find the derivative of an implicit function is a little bit different from the way you find the derivative of an explicit function. Just as a reminder, explicit would be something like y equals, I'm not going to use this exact example because that would be a little bit confusing, 10x cubed. A minute ago I wrote y prime. There is another notation that you can use for the derivative, dy over dx. Yes, you all familiar with that? Okay. So you could write dy over dx equals, and it's real nice and easy because you're going to take the derivative of this. So we know from the power rule, this would be pop down the 3, so 3 times 10, so you got 30x squared. And you're done. That's explicit. When you have implicit equation, things aren't so easy, okay? You've got x squared plus y equals 5. When you do implicit differentiation, it's like this. You take the derivative of the whole left side and you take the derivative of the whole right side. And you're like, okay, do you have a symbol for taking the derivative? Yes, we do. That symbol is d over dx. that means, I'll put a little note here, take the derivative. So, take the derivative of x squared, James. Ding, ding, ding. Ivan, take the derivative of y. Yeah. You're like, I don't know what y is. You didn't explicitly tell me. Okay? But who cares what it is? I'm going to write this right here, dy over dx. Because we know that that symbol right there is a reference to the derivative of y.
So, whenever you're taking the derivative, it's d over dx. But as like kind of like a placeholder representing the derivative is dy dx.
Yeah, this is a command.
Okay.
This is take the derivative of what's over here with respect to x.
The dy
It's
dx
not-
is like this is in the place of this is the derivative.
Yeah, like this, yeah, that's what this is representing. This is representing the derivative. It would be wrong for you to think that all we did is multiply the d times the y and the dx. That is not, it's really unfortunate that it kind of
It
looks
looks
that
like that,
way,
yeah.
but that is not at all what's going on. Okay, well this is a command, which is take the derivative. Yes sir, took it, 2x. Take the derivative of y. Yes sir, it's dy over dx. Because we always know that the derivative of y could be written as dy over dx. There's some textbooks that instead of, when they teach explicit or implicit differentiation, they put y prime right here. But I think that's even more confusing because y prime looks a whole lot like y to the first. Darn you mathematicians. There you go, there's y to the first, kind of broken, but there's y prime. Alright, dy over dx is the way to go, okay? And then, Ivan, keep talking to me. Take the derivative of 5. Yeah, 0. Okay, and then if you wanted to, with your implicit, you could subtract 2x from both sides, and I would have dy over dx equals negative 2x. Notice, at this point, I have an explicit derivative, which is good. It's just telling it like it is. There's the whole dy over dx, even though I had an implicit function where the x's and y's are all kind of mixed together. As a guy, I like explicit things spelled out right there. You tell me. I don't want any games. I don't want any hidden meanings. Okay, ladies? All right? I know I'm being ridiculously, categorical. I don't know if that's the right word. I don't like patristic. It's just patriarchal or anything like that. It's just make it a joke. All right. I think we have enough background to be able to attack this problem now. 7x squared plus y squared equals 9. I'm going to first just take the derivative of both sides. D over dx of 7x squared plus y squared equals d over dx, so take the derivative of 9. So I'm taking the derivative, I'll take the derivative of each term. Randa, while we're talking here, what's the derivative of 7x squared?
14x.
Yes. So she popped down the 2, 7 times 2 is 14. Power down the 2, so it gets the first, but she's not going to say that because we don't say it. Now, this is where it gets weird. We take the derivative of y squared.
Do you make that 2 dy dx?
Mm-hmm. Yeah, but the question is why?
Because you dropped down.
Because I would be like,
Because you dropped down your exponent.
But then
Okay.
why still like a
And that's why I
constant?
want.
okay, so yeah, so it's 2y to the 1. So we're kind of treating y like its own little like sort of world right there. You know, because it is. It's got some sort of y equals whatever. So yeah, so we're going to pop down the 2, and then we've got y to the first. So I'm leaving that. Okay? But then I have to apply the chain rule, which is I have to then multiply it by the derivative of what the inside is. Are you all familiar with the chain rule? Have you heard that
Wait,
phrase?
to do what? You have to multiply by the.
pause. Need to teach
The
you
homework
about-
you mentioned the chain rule, but I haven't known it.
Okay, let me tell you what the chain rule is here, okay? I'm pretty sure you probably know the product rule and the quotient rule, okay? The third one is more powerful than both of them because it allows you to combine all of them, okay? So let's talk about the chain rule real briefly. The chain rule deals when you have functions of functions, okay? So, no big deal, 7x squared, okay? But what about this, Rigel? Parentheses, 7x squared plus 5x, all to the, something ridiculous.
Is that the one you do n minus 1?
8.
Is
N
this
minus
the-
1 is what you do with the power rule.
Oh.
You could apply that very same principle here in a minute, yes.
Is this the derivative of f of g of x times the derivative of g of x?
Yep. Like, what in the world? Does anybody feel like multiplying this sucker out 8 times?
Nope.
And then, you know, foil, and then do the power rule? No. Here's what you can do. You can treat this whole parentheses like a hand. Okay? Just like a block. And so you can say dy over dx equals, now we'll do your pop down, power down with the blah hand. Okay? So pop down, Kevin, 8 times blah hand, 7x squared plus 5x. Power down, 7. But you're not finished yet. This is where the chain rule is, okay? You then have to multiply this times the derivative of the inside. Okay? So the derivative of the inside is 14x plus 5. Derivative of inside. So the chain rule can lovingly be remembered as the derivative of the outside times the derivative of the inside. And you have to think, what's the outer function, okay, which is blah to the 8th, times the derivative of the inside, which is going to be all this. In pre-calculus last year, we had some problem sets that said, write this function as a composition of two functions, where the outer function was x to the 8th, and the inner function was 7x squared plus 5x. You may not remember that, but we did it. And so that was designed to get your mind to start thinking in terms of outer and inner functions. Okay. I think another polynomial example might be a little bit ridiculous, but we'll do one with sines and cosines because that's something that you'll probably see later on. I'm really liking this 5x. So here we have y equals sine squared of 5x to the 4th. If you remember, when you have sine squared right there, what that really means is sine of 5x to the 4th, and that whole thing is squared. So therefore, dy over dx equals, what is the outer function? What's the inner function? Make it even easier. Anybody? What's the inner function here?
20x to the...
Now just tell me. No.
Oh.
Actually, there's an inner and there's an inner. This is triple layer here. The innermost layer
The inner is cosine
would be this
5x.
one right here, 5x to the 4th. Then you'd have another layer here, the sine of 5x to the 4th. And then you have an outer layer here, blah, x squared. Does that make sense? So it's like a triple layer here. So it's going to be, so the derivative of this is going to be the derivative of the outside. So you have to look at the outermost thing. The outermost thing is hand squared. So it's going to be 2 times hand to the 1st. So that's just going to, so the inside stays intact. Sine 5x to the 4th. But then you have to do the chain rule. So times the derivative of the inside.
So is the inside sine 5x to the 4th?
The inside function is sine of 5x to the 4th. So the derivative of sine of anything
Is cosine.
is cosine of the anything.
Would it apply if it's originally cosine? Would
If
be
it was
sine?
originally cosine, it would be negative sine.
The derivative of cosine is negative sine. What you said is correct. That is something that I'd recommend you have memorized based on looking through the rest of the test. You need to have the 6 straight functions as derivatives memorized. Alright, so, but wait, there's more.
Do you have to do times the inner?
We have to do times the inner. So that's going to be 20x cubed. Popping down the 4, multiplying times the 5, 4 times 5 is 20, and then power down, and you get 3. Alright, great, there's chain rule.
Okay, so I understand the chain rule, but why does that apply here?
Great question. Let's go back to this one now. So, here we have y squared, alright? We're treating y like a block, like a hand, okay? So you take the derivative of it, it's pop down the 2, got it? Then you have the y to the first, then chain rule, times the derivative of the inside. Because the derivative of, because y is not a single variable itself. Y is dependent upon x. So there's really, I mean, instead of y here, we could really put blah, 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 it's not x squared times, 5x plus 3, I mean, there's a whole lot of other stuff going on inside that y. We don't know what it is because they wrote us an implicit function rather than explicit. So we're like, okay, I can handle that. I'm just going to write dy over dx, so whatever it happens to be, that's going to be what the derivative is. Does that make sense? So we had to kind of figure out what the chain rule was. And you have to use the chain rule when you're doing implicit differentiation problems.
So when y stands alone, you always do chain rule, because it's not really.
Because, yes, because you're taking the derivative with respect to x, and y is dependent upon x. If, for whatever reason, I had said find the derivative with respect to y, then everything else would be kind of funky. But this is saying find the derivative with respect to x, no big deal, and so we've got that. That is going to then equal 0 because the derivative of 9 is 0. Say it again. I am, because I'm gonna want to isolate now. If I write steps down, the next step would be isolate the dy over dx. So I can do that. I'm in calculus. I can do this all in my head. I can say negative 14x. At the same time, I'm going to divide both sides by 2y. So dy over dx equals negative 7 times x over y. I could put negative 7x over y, but you'll see here in a second it's going to be helpful to have it written like this. Okay, so that's one implicit differentiation. Of course, this problem has going to then require us to do it again, which is good because we need the practice. Does anybody still have a question about the chain rule? Derivative of the outside times derivative of the inside? Okay. Since we're talking about rules, and this is a review session, we might as well, and we're going to need one of these in a minute, review very quickly the product rule and the quotient rule. The product rule is when you have a function f of x equal to the product of two other functions, g of x and h of x. So an example would be like f of x equals x cubed times sine x. The product rule says the derivative is the first times the derivative of the second plus the second, it's the second function, times the derivative of the first. In symbols, that would be g times h prime plus h times g prime. But I feel like it's always easier to remember the first times derivative of the second, but the second times derivative of the first. Try it with Kevin. The first times the derivative of the second. Say, repeat after me.
First times the derivative of the second.
Plus the second times the derivative of the first.
Plus the second times the derivative of the first.
Okay. Yeah. I recommend that you. Let's all say it together. All right, everybody together. Repeat after me. The first times the derivative of the second.
The first times derivative of the second.
Plus the second times the derivative of the first.
Times the second times derivative of the first.
No, you said it's really plus. Plus the second times the derivative of the first.
Plus the second times derivative of the first.
Okay, no big deal. Okay, so applying that over here, the first, x cubed, times the derivative of the second, which we now know derivative of sine is cosine, yep, plus the second, so sine x, times the derivative of the first,
3x squared.
3x squared. Remember that 3x squared is on the outside, it's not inside that sign. Okay, so there you go, there's the product rule. We're going to get to review all three of these. Any questions on the product rule? Alright, what about the quotient rule?
Oh, isn't that the G, wait, I have to count something.
It's like the product of x minus
Over
over
each
over
over
the
each over each of x.
and the second one.
Derivative of denominator times the numerator minus the derivative of the numerator times the denominator
So we can have the
over the denominator squared.
Right, okay? So, you can think of the it's when you have a function over a function. I call this one high and I call this one low. And the formula is low d high minus high d low over low squared we go. Low d high minus high d low over low squared we go. It's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator divided by the denominator squared.
I like this,
This way is a fun way.
Yeah.
It is. So repeat after me. Low d high
Low D high.
minus high d low
Minus high D low.
over low squared we go.
Over low squared we go.
Yeah, see? So no big deal. So an example, f of x is equal to x squared over cosine of x. So I always want to start with the numerator. Like, it's going to be the numerator. No, it's always the denominator. Start with the denominator. So it's low
Times
d high, so 2x,
minus
minus, because it's weird, because it's quotient,
x squared.
x squared times
Negative sign.
negative sine x, because the derivative of cosine is negative sine, over,
Cosine x squared.
yep, cosine of x. You can put that in parentheses, put squared, or you can put the squared right here between the cosine and the x. It's fine for right now. Okay, over low squared we go. I could write that in symbols, you know, g of x times h prime of x squared minus h of x times g prime of x squared, you know, but you probably already have that written in your notes somewhere. This is nicer. It's different. Okay. We had to discuss the product rule for review purposes. We had to discuss the quotient rule because we're about to use the quotient rule right here when we take the second derivative. Any last thoughts on quotient rule? All right, here we go. So let's apply it. So we're finding the second derivative. So d squared y over dx squared is going to be the derivative of this. Okay? It's the derivative of the derivative. Now, other rules kind of make your life a little bit easier. If you have any number times something else, well, and you're taking the derivative, you can just essentially pull that constant out front and then take the derivative over what's inside, the other part, okay? So that's why I wrote that -7 out there, because I knew we were gonna go over here, take the derivative of this. So here we go. So -7 times, everyone say low D high?
Low D high.
Alright, so low is y. What's the derivative of the numerator? 1. Repeat after me, minus high D low.
High D low.
So minus high, so that's x, times dy over dx, because the derivative of y is dy over dx. Repeat after me, over low squared we go.
Over low squared we go.
So, over y squared. So that's going to be -7. I'm going to pull out this y squared because I want to. Times, y times 1 is just going to be y. Minus x times dy over dx. Now, dy over dx, hey, I know what that is. That's this guy right over here. It's -7 times x over y. So, -7 x over y. So I'm substituting in, I'm doing a lot of this stuff kind of all in the same step just for time's sake here. I pulled the y squared out here, and I'm substituting in -7x over y. And the reason I have to do this is because the answer that they're looking for is something simplified in terms of x, if possible. Okay? So I'll write this. Now it's just an algebra game. -7 over y squared times y minus, well, hold on, minus and a minus is going to be turned into a plus. So that's going to be 7x squared over y. I'm going to multiply this term right here times y over y to get a common denominator. So that's going to give me -7 over y squared times y squared over y plus 7x squared over y. So that's -7 times y squared plus 7x squared. I'm going to just pull this all over y, but that y over here I can put it as a y cubed. Okay, and you think you're done, but I guess they want it all in terms of x's and y's, and for whatever reason, I don't know if my math lab would accept this, okay, but they don't want this. This is not what the answer they provided, because what they did is they say, okay, 7x squared, if you look at this original equation, I can manipulate it by subtracting a y squared from both sides so that I have 7x squared equals 9 minus y squared. And so I can substitute that in for the 7x squared.
But isn't 7x squared plus y squared equals 9, so couldn't you just put 9 in?
Yeah, okay, I can put a 9 in there. That's even better than what I thought. Yep. I can put a 9 in
Oh, that. Okay.
right there. Yeah, even better. I hadn't thought of that. So here we go. So I'll put it right down here. Equals -7 over y cubed times 9.
Why do you put the 9?
Because looking back at the very original equation, 7x squared plus y squared equals 9. So I did that substitution here, and so I get -63 over y cubed. Based on the fact that the algorithm and the computing programming that they use to generate all these questions is kind of the same, I would assume that on your test it will require a similar substitution. Okay. Just to recap what we did here, this was an implicit function, and so we had to apply the chain rule right here. We solve for dy over dx. Then I pulled out the 7 to make my life easier without having 7s everywhere. We applied the quotient rule. And then also once again with the chain rule with the dy over dx. Then we substituted the value from the dy over dx in here. Did some algebra to make this other term go away, just trying to find a common denominator and so on and so forth, and that got us the second derivative. And so those are the easy problems.
How many questions?
I thought they were easy because they're just straightforward applications of this. Then we review all this stuff. Some of the other ones that I think are longer, but shorter. I got 20 questions on this sucker. All right. Some of them are legitimately shorter than that, but I go and chase these rabbits. So. And number